hand side of the optimality equation, and this is like the sort of the right-hand side.
Yes, yes.
So this is like your, you might call this like the Bellman error or something. So you take a step in, you adjust your current estimate according to this error. So if this is, yeah, so if, uh, yeah, I think that I think, I mean, you can write this differently, in terms of, yeah, but
And alpha is close to 0 to 1.
so alpha here plays a role in, uh, it's relevant to convergence in the sense that in general, if your step sizes are too big, things might look too erratic. If it's too small, your progress might be too slow. So this is related to, so for convergence, I think usually there's some kind of like, these vary with the step, and you have some like Robbins-Monroe type.
Yeah, yes. Statistical approximation, yeah.
Yeah. Right. So this is Sarsa. So
So
then,
basically, for SARSA, you have a policy, yeah, and when you visit, you recalculate. But do you change the policy that you run?
yeah, yeah. So the policy that you're following throughout is going to depend on your current Q-value estimates. So as your Q-value estimates change, your policy is going to change as well.
Mhm. What about Q-learning?
Yeah. So Q-learning is exactly the same except for one difference.
Mhm.
So that difference happens, is essentially here. So here, note that we took an epsilon greedy action with respect to Q at our starting state, and then we observe the realization of the reward in the next state. And then we select another epsilon greedy action. So now in Q learning, the only difference is that we don't select this second epsilon greedy action. So in particular, if we look at Q learning down here, so just going from the start of a given time step, you select an action that's epsilon greedy with respect to your current Q estimate, and you observe the realization of the reward at next state. And then in Q learning, the difference is that you immediately go and update your Q value estimate. And so the target here, so the difference is, instead of here, we selected an epsilon greedy action with respect to our next state, and then we used that action here. The difference is that here, instead of doing that, here kind of the thing that's in the quote unquote target is this. So from our next state, we just do an arg max. So or we just do a maximization there. So we don't do another epsilon greedy here. So it's sort of, in a sense, always greedy.
Jefferson, I don't quite understand. So when we run, we recalculate Q with the same policy here, and there we select the maximum A.
Yeah.
In one place, we select whatever the current policy says, yeah, and in another one, we select the optimal value, yeah? This is
Yeah.
the difference, yeah?
Yeah, so it's in that sense that SARSA is sometimes referred to as being an on-policy algorithm, and Q-learning is off-policy. I think it's because here, yeah, you're not, in a sense, selecting actions according to the same policy.
Mm-hmm. So, and Q-learning is better usually, yeah?
It seems to be more widely used. Yeah.
Now, what do we use? We use a version of SARS or we use a version of Q-learning?
Based on the documentation, it looks like it's a version of Q-learning.
Version of Q-learning. Okay. And Thomas, can you please show me the description? I'd like to try to understand the relevance of the formulas in Q-learning with they have some squares there that I don't understand. I don't quite understand.
Like this page.
Yeah, this formula, for example, LFID, what is it? Is this some kind of error?
That's the loss, right? Yeah. So it's the difference between the Q function of the current state and then what we would expect it to be based on the Bellman equation.
Now, in reinforcement learning, are there algorithms that similar to value iterations?
So I think Q-learning is pretty much value iteration.
But in Q-learning, you still have policy. You go from one state to another following the policy.
Yeah, there are there's something called fitted value iteration.
On what step you improve policy, on the second step you improve value, greedy. Oh, sorry.
Okay, now, may I ask you a question? In this world, what is TD learning? Or TD learning, what is this? Temporal difference.
Temporal difference is, sorry, can I show my screen one more time?
Yes.
This is a very simple. The very good explanation is given in Satan Bartov, for example, here. What does it mean, temporal difference? This is the regular way how to improve values. And this is how to improve it by temporal difference. What's the difference? Difference the return. You do not need to count a return here. You replace it by the one step reward plus discounted value of the next state. What's the difference between regular update and temporal difference update? And here you do not need to get GT, and so you do not need to use Ionesco-Tulce theorem to compute GT or something.
What is GT, Pavlo?
No, GT is the return.
Yes, and RT?
RT is the recent one-step reward. This
what
is
the difference between reward and return?
Reward plus gamma multiplied by the value of the next states. This is the same as, no, this is approximately the same up to the expectation to the return. The discounted rewards starting from the initial state st, Bellman rule.
Yeah.
Bellman rule, Vt plus 1, for example, of pi equals one step reward plus discounted value, roughly speaking, from the next state.
Pavlo, this is a problem of minimization or maximization?
No, here maximization, but
and V is the value, yeah?
Value or total reward, for example, or discounted reward. V here is the estimation of it. frequency. But
So let me ask you, in an ideal world, what we have that V of st equals RT plus 1 plus gamma VST plus 1, yeah?
no, roughly speaking, yes.
Yes.
Very roughly
And
speaking.
yes, and why is this true that this difference is probably positive? I'm asking why it is positive.
No, they
It
decided
could
such.
be positive or negative.
And I need to mention that this algorithm is given for non-autonomous problem. If you want to consider autonomous problem, you need to use not constant alpha. You need to use alpha depends on choose of A, for example, and which satisfies some big number theorem or
Yeah,
something like
yeah.
this.
Just a second. You use autonomous, autonomous, and the same things that some of us just used online, offline, yeah?
No, in
No?
all algorithms they give alpha constant to make it adaptive to the change of environment in time. No, in the problems you usually have the following situation when the environment changing in time, and so they need to consider some alpha depends the choose of alpha means the range of interval range of the memory. For example, alpha equals to 0 means that you have a very short memory, and alpha equals 1 means that you use the total memory. And
Oh, it is like in forecasting.
ну да,
Like in after regression.
yes, after regression, this very, if you have if you have no control, you have after regression with these formulas. Exact.
I see. I see. So this
So
is
how to find a right value for alpha in our problem, and the length of horizont is a very important problem.
so when you call non-autonomous means that the environment changes, yeah?
Yes, when environment
So
doesn't change, this algorithm doesn't converge, because in the big number law you need something like that for alpha t. The sum of alpha t need to be equal to infinity, but the sum of alpha t in square need to be equal, need to converge. But alpha constant, the second moments are do not converge. Alpha in square plus alpha in square plus alpha in square, etc.
yeah.
Equals to
You need something like 1 over n.
yes,
That
yes.
the squares converge and it goes to 0,
For
yeah.
each state and for each action that you choose. It's no, rather difficult to realize, but it is possible to do. But in the deep learning version, to realize this is more difficult, but also possible.
What is more difficult in deep learning?
Because you have also some approximations, and for example, via neural networks or something like another methods, and because you have finite number of states and actions that you can visit via one episode, but if they are, for example, uncountable, continuum or interval states, or more difficult, you need to make some approximations. In more cases, it is, no, like in our case, it is unparametric problem. So you need first of all to consider some parameterization, and then you can find you can make some algorithm. Therefore, I think that the business that make Thomas in the last couple of days is very important and very difficult, because we have now to set the parameters in that way that the solution needs to be physical, but all that I saw is rather close to that we need. Of course, there is some errors, but if you provide graphs, not line, for example, but histogram or something like this, it will be more understandable to see that his progress is very effective.
So,
He need to rewrite some, I think he need to rewrite some pictures, not line pictures, but make something like histograms or some, for example, if there is wrong monotony, he can give here a line and make, for example, piecewise approximation, piecewise constant approximation of his pictures, for example. And
Thomas, do you understand? I don't.
Yeah, I'm not completely sure. You mean a histogram for the Q function?
For the graph of solution, you paint for each horizon, you paint the strategies. Yes, you paint
Thomas, maybe you can show the picture, maybe other pictures, because here we have only horizon 4.
For example, 4 we saw also 16, as I remember. Maybe
Yeah.
So you mean like this graph, but a histogram?
Yes.
Yeah. For example, what is this?
I started running another training with Horizon 8.
This is, as I understand, this is a version of SS strategies. But if we will draw this picture, for example, we will make, for example, some approximation of this result via piecewise constant functions, we will obtain something very close to SS strategies, I think.
We may not have SS strategies here at all.
We have here one product, so I think SS strategies will be optimal strategies. But I can
No. This policy, I don't think so.
in one product, not SS strategies.
No. It's incomplete information. No. It's not.
But of course, let me see.
Now, Thomas, what is here the discount factor?
Let me check. Is that 0.9 or 0.99? Discount. 0.9.
0.9. Okay. My question is, if you make not 8 steps by 32 steps, will you get something similar?
Yeah, it will take longer to train because each episode will be longer. But I think I did 32 before and I didn't notice any improvement.
Can you show the picture for 32?
Yeah, it will take some time to train, but I can start it.
Yeah, but it will be reasonable, or it will be.
I have to change it.
Hello. I
There's
can,
some
at the end of the talk, I can just briefly mention it and briefly show it, and then that we just started, yeah?
Yes. But I think this is a very good job, and we need to proceed it.
No, this is I don't like at all.
No, not today, but in
No,
general.
I mean the picture. I'm talking about the picture.
Yeah,
How
that's just
Yeah.
after one training episode, so doesn't really mean anything.
I think that if we will choose another format of picture, it will be no. But these pictures are very good.
Show me for n equal 8 again.
Mhm.
Here. Okay.
Yeah, doesn't make much sense as well. Yeah, I don't know.
So I think Pablo mentioned early in the call that, or sort of alluded to this question of whether here are we applying this algorithm to the, are we applying this to the completely observable MDP that we get?
No, we completely.
Okay.
Yeah, I think that's an important thing to discuss. So I'm storing each state as the list of past actions and past observations because that's what determines the belief state. What I tried to do, I thought this would help. I made it so it stores the most recent observation in the first spot of the vector, because then it's always learning I should do this if this was the most recent observation, but that still hasn't caused any improvement. And then, so it stores the actual state, but the algorithm doesn't learn the actual state. It computes the state so that it can calculate the reward.
Can you show it for 8 again? For 8, there was a picture was reasonable, I believe.
Yeah, it kind of comes up with something different every time. So.
Oh, okay.
Yeah.
Yeah. So my impression is that this is variability, a large amount of variability in what you get in terms of outputs. It's a well-known phenomenon for these kinds of things. So yeah, maybe I don't know, just seeing whether if you just let it train for longer, whether it settles on something.
How long is longer? Because I've done like several thousand episodes.
Yeah, I mean, it could be that there, like a priori, it's sort of hard to say. So maybe just let it run for a long time, and then like the histogram idea, I interpret that as like you have on the same like XY axes, where the x-axis is the observe is it here
here I have it the initial state.
So then you would just have like I mean, one way it'll be pretty messy probably, but just like having one, you do this whole process for over multiple runs. So you train it to like 1,000 time steps, and then you look at the final graph, and then you train it for another 1,000 seconds or something, and then you have maybe a different graph, and then maybe see if there's any whether things are settling down. I don't think it would be that surprising if it doesn't. But yeah,
Yeah, I mean, I feel like I've done essentially that because, well, I have it print out like this graph like repeatedly, and I've let it go for like up to like 4,000 episodes, and it doesn't go down.
What is this? What is this graph?
This is showing the total reward. So like it will run an episode of 8 time steps and then calculate the total reward. And I have it print out the time steps here, so you can see.
It is the distribution of the total reward.
Yeah, so ideally it would be going down eventually and like converging.
I think that here is some such variation, a big variation, because no big volatility, because you take a constant alpha. I think if we will try to do this more, to try to choose it in a such way that
Alpha equal 1 over n, for example.
no, yes, but alpha equals n for each
1 over n.
yes, but it's this is the n is the number of choices of the action, but in the deep version of this algorithm, I do not. No, you need to do this. We need to think. Yes, but the idea is to try also such situation if it is possible here. Yes, because with constant alpha, it's more appropriate for programming, but maybe it have no time to learn here because he goes out and no, such volatility is, I think it connected with this, but I can be wrong, but I think we need to try also such version which converge. Why? Because the number of length of episode is very small, therefore it have no time to, and it have no enough time to learn, I think. But okay.
Thomas, do you understand Pavlo's suggestion?
I think so.
No, it's not connected to the length of. It's not connected to the length of episode, but if we will try, I do not think that it would be. No, I think we may try and see.
Yeah, I think the main thing is just adjusting the learning parameters.
Maybe Jefferson have more experience in such problems, and he maybe can advise something here, because I have only one idea.
Yeah, as far as I mean, really, as far as like learning rate schedules, I don't really have much to offer in the sense that I think for the problems that I've applied it to, they were simple enough that a fixed learning rate was sufficient to get to for it to actually recover the optimal policy. I know there's a lot of I think there are a lot of papers on this stuff, like learning rate schedules. And I guess here in the reinforcement in the setting we're using neural networks, there might be some things that are specific to that too. Yeah, so nothing, unfortunately, I don't have anything concrete to offer.
I thought maybe with a smaller horizon, it would learn better because there's not as much information to learn. But as Eugene was saying, it's not a very realistic problem with a horizon length of 2.
Would it, if the horizon length is like 2, it's just like a, if it's 1, is it just a news vendor problem?
If it's 1, there's no point in having the fixed cost amount really, because it will just not order if you make the fixed cost too high.
Can you show this picture? No, that's the good. Okay, so
can you show the averaged result? For example, not each value, but for each as I remember, for each episode, can you average it? For example, from previous to the recent one, and draw such picture. It wouldn't be so it will be smooth in this situation. And then to give it to Eugene, or
the average of this
of
the
values.
policy?
No, average of values in dynamics. No, I mean, what does this picture means that we see now? This is for values, yes. This is values.
This one? This is the total reward.
Oh, total rewards. And can you draw such pictures that at each episode gives average from the initial to the given one, and then you will have a smooth curve for averages, because you have.
I don't understand. So the average.
I mean, what does I mean? Can I? Yes. Can you see me now? I will write desk.
So let's take it out. Pablo wants to place his.
Should stop sharing.
Yes. What does it mean? For example, you have a graph here. For example, number of episode 1, episode 2, episode 3, etc. Episode, for example, 18, and here the total rewards, yes. For example, R at this episode, R at this episode, etc. Yes, and I propose you to write the following. For example, here will be sum I from 1 to t, rt, to draw such function. Besides rt, to draw sum of rt from 1 to t, re, divided by t. And when you will draw such function, it will be a smooth curve.
Okay.
Thomas, do you understand? Did you understand?
Yeah, I think I understand. So it's the average of all the rewards so far
Up to the current episode.
And what will it give to us?
It will be a smooth graph
Of what?
of rewards in time, or not in time, in episodes. No, for example, for 10 episodes, for 1,000.
No, I understand, but how you translate it to the optimal policy, optimal value?
This is the approximation for optimal value. When the number of episodes converge to infinity, these values converge to exact value.
Okay, so can
the optimal value.
Can we draw the optimal reward order number?
This is another question. Now we draw the optimal value, but no, it's approximation. For example, for some initial state and maybe and possibly action. But if you want to draw optimal policy, you need to do it more. I propose to start from the optimal value and then to think about the optimal policy. What to do in such situation, I have no answer yet, but we can also think about it after. For example, I think one possible way to draw optimal policy is to correct the picture that Thomas did. For example, you can for example, if you have some optimal policy like this, you can correct it by your hand. For example, you want to see this and this, for example, and something like that, and then he will correct it, and or he can draw these lines in different, for example, in different color, and you will say that this is approximation of this exact, for example, version of the optimal policy for this problem of something like this.
So what Pablo is saying that in fact the problem is discrete. So we see continuous approximations of discrete things. Yeah, that's what we're trying to do actually, but it didn't lead to anything good.
No, I do not think so. He may make his picture discrete and write something like that. That this is approximation for optimal policy, for example, up to such parameter, or this is epsilon with some epsilon optimal, or this is approximate value or something like this. I think it would be enough for the conference, but of course we need to finalize it in a time. For example, in a week or in a month or somewhere.
Jefferson, have you seen such discussions before?
Not exactly. I don't quite understand the approximation of something discrete with something continuous. That last point, that like how are you, like, what are those horizontal lines?
No, the situation is that the policy is SS policy. And the software tends to smoothen things. So,
Of course.
So here, but in the incomplete, so we're in the incomplete information setting. So are we?
no,
Yeah,
it's not exactly as a policy. We don't have this result in a complete setting.
So the
It's basically if, for example, the policy is SS policy.
It should be something like an SS policy.
Okay.
But we're not sure. We don't know.
Yeah.
But I think like the algorithm is perfectly capable of approximating the discrete. It's not really discrete, but it's not a continuous shape, like fully continuous. And in some cases, it has been able to approximate that. It's just not consistent.
Okay.
I made the graph that Pablo was saying. If you want to look at it real quick.
You can do it right now?
The one with the average.
Yeah.
Yeah, I can show that one.
Okay.
Yeah.
Fantastic.
So it does look a little bit better.
No.
At least
What
it's
is
going.
this?
This is the average reward over all the episodes, like up to that point.
Look realistic because temporal difference or Q-learning they have such effect that we can in some situations, in some episodes, converge out of the optimal values. So we have, but when the number of episodes became rather big, we see the rather stable situation.
Thomas, do you have an idea how to extract an optimal policy from this? Or how the optimal policy would look like?
He can try to do the same, but I'm not sure that if in each episode he possibly if the optimal policy is not unique, for example, in different
No,
episodes.
it will be unique, of course, because
If it's unique, if it is unique, you can try to do the same. You can try to do the same and look at the result. But of course you need to average all the graph. And I do not. You can use a recurrent formula, for example. The new function, the average for new function is the average of previous multiplied by n divided by n plus 1 plus 1 divided by n plus 1 and multiplied by the recent function. And if you will do such average for number of episodes and draw the result, that or you can simply average the values and divide by the number of episodes you do, and to show us the result. Possibly it would be also more regular.
Did you understand it?
How is that different from this?
I think it's different from this. Can I draw it on a black box?
Yeah.
I mean the following, that at each episode you have some policy. This is a graph, for example, for phi 1, graph for phi 2, etc. What I propose? I propose to draw, if you have, for example, 300 episodes, I propose to draw the graph of the following function. Sum from I from 1 to 300 of phi e of s divided by 300. On this way, you need to check whether you have with the appropriate numbers to do not contain maximum, like int 32, for example. You understand that?
May I ask you a question? Maybe we should sum from 1 to 300, maybe from 100 to 300, because maybe in the beginning they generate some jump.
This is a very good idea. For example, from 100 or 1000, no, from 100, of course, to 3000, no, something like this, of course.
Yeah, last window,
the last, of course. But if from 100 to 300, you need to divide it by
200, yeah.
No, something like this. But when you will compute this formula, you need to be sure that you do not exceed the maximum value, because in this no, I mean PEP8 you need to
Do not have overflow, yeah.
yes, overflow, to do not to avoid overflow.
Yeah. Thomas, is it understandable?
Yeah, I understand. I'm not sure if that graph will look any better considering, but
Let's try.
yeah. I'll try it.
You can do it right now? Right, yeah.
It might take me a couple minutes. Let's start.
And when you draw the previous graph, you need to mention for what initial parameter, no, for what initial state you draw it.
This one might take me a little bit more time to code.
uh,